of ways that dark matter could have been produced in the early universe. I think we had I had a list of 4, and somebody added a reasonable 5th. But one of those 5 mechanisms is a basic picture where we have something that starts out in thermal equilibrium, and as the universe expands, the mechanisms that keep it in equilibrium stop being efficient, and at that point, the number density freezes out of equilibrium, leaving us with a thermal relic abundance. This isn't the only way that dark matter might have been formed, but it is certainly among the best motivated, if not the best motivated, and you can construct any number of particle physics scenarios in which you get an acceptable abundance of cold collision of this dark matter through this process. So then we went on to calculate how much dark matter would be formed in this way. And for the case of a cold relic, which of course is what you need in order to explain large-scale structure, we learned a few things. First of all, what's the sort of mass range that we said a cold relic that makes up the dark matter abundance could be found in? Were we out too late last night? Is this a problem? Oh, okay, so what's the minimum mass that we can consider and why? And why? BBN. Okay, if you have a thermal relic with that annihilates at a time below the temperature around or below the temperature at which the light elements are being synthesized, you will screw up those predictions, and those are very robust, and you don't want to have anything like that amount of energy being deposited in the universe during BBN. Or even if you want to go to something like neutrinos that won't necessarily disassociate the nuclei, you still have to worry about changing the expansion history with all that radiation. So you can't be lighter than about 10 MeV. You can quibble about whether it's 8 or 12 or whatever, but about 10. What's the upper limit, approximately? About 120-ish TeV. Basically, you can't write down a self-consistent quantum field theory where dark matter can annihilate enough if it's that heavy to avoid being overproduced in excess of the measured dark matter abundance. Okay, so we have this range of masses that we can consider. It's a lot of orders of magnitude. I guess it's well, it's not as many as I thought. Okay, it's about 7 orders of magnitude to target. So we're going to have that in mind when we talk about indirect searches. We're usually going to be talking about anything from GeV to TeV scale particles, sometimes lighter, sometimes down to MeV. What's the other aspect of this calculation that informs us as to where our motivations or benchmarks should lie? What else does the thermal relic abundance calculation tell us about what we should expect the characteristics of dark matter to be? Nope. So that when doing the relic abundance calculation, we came up with in addition to the mass of the dark matter, we said we had a reason to expect a certain quantity would have an approximate numerical value, cross-section. And what number is that? Yeah, that's about right. And you should kind of have that number in the back of your head throughout this set of lectures. You said 3 times the minus 26. I think it's more like 2, but fine. Let's not quibble. And it depends a little bit on mass. But and I do want to emphasize that number can be quite different depending on models and things. And we'll probably Thursday-ish, we'll go through a bunch of those exceptions and explain what impacts that number and things like that. But we're going to have in mind that what we would like are a class of experiments and observations that would be sensitive to a particle in the mass range we're talking about, and with a cross-section in the ballpark of 2 times the minus 26 cubic centimeters per second, and would be able to detect the various forms of annihilation products that would produce. Okay, that's the end of the recap. So now we're going to talk about gamma ray searches for annihilating dark matter. We started this a little bit yesterday. I'm going to write down one equation again from yesterday just to repeat that. So the differential flux in a solid angle that we're going to observe looks like this. so far we haven't specified a target or anything. This is a generic equation that's valid so long as you're not worried about things like redshifting and absorption, which for anything in the local universe is perfectly fine. This whole quantity is usually referred to as the J factor. There are slight variations in the definition of the J factor in the literature, but this all just has to do with how you normalize things. They all basically have to do with a integral of the density squared over some volume that you're observing. And if you do that integral, you'll find that this scales with the density squared times the volume of the thing you're looking at over the distance to that thing squared, just as your intuition would lead you to expect. So next, we started to talk about what features you might want in a target for a gamma ray search for dark matter. And we said there were 3 features you would ideally like. You'd like something that is highly dense in dark matter. After all, the annihilation rate in a volume goes like the density in that volume squared. Secondly, you'd like a source, or a target that's relatively nearby, because after all, the flux that you observe from a given source goes like 1 over the distance that source squared. And thirdly, you'd like a part of the sky to look at where there isn't a lot of complicated backgrounds. Okay? So the signal goes like density squared over distance squared, and then the backgrounds depend on a bunch of astrophysics. And I'm going to make a highly scientific set of axes here. And we're going to put different targets where they fall roughly in this plane. So I'm sure some of you have thought about these sorts of things. What's an example of a gamma ray dark matter target, and where would it fall on this plane roughly?
Galactic center.
Okay, so tell me where on the plane the galactic center falls and why.
Lots of backgrounds, high signal. So high signal because it's more dense in, say, dark matter. But there's also a whole bunch of stars and random stuff.
Good. I agree with all that. So just to repeat, the galactic center is definitely supposed to be the brightest source of annihilation products on the sky by a large factor. It's just a ton of dark matter, and it's not very far away. On the other hand, there's an awful lot of gas. There's an awful lot of cosmic ray production. There are a lot of point sources that we don't know about and haven't resolved. All of those things make it difficult to separate signal from background. So let's go in the opposite direction. What's the target people talk about that is generally considered to be the cleanest? Dwarf spheroidal galaxies, right? So does anyone have a ballpark estimate for how high this flux is compared to that of a given one of the brightest dwarf galaxies? What kind of ratio are we talking about? Talking about a factor of 2, a factor of 1 billion? What are we talking about? Yeah, thousands to tens of thousands is about right. So the dwarf galaxies are really much, much fainter, but they have very limited backgrounds. They have about as ideally low backgrounds as you could hope for in a target like this.
They're only fainter in that the total emission is expected to be smaller, right? Like if the resolution of a like Fermi would, if I can look at a dwarf, I look at the galactic center, I can resolve it as well. I expect 1 pixel of a dwarf to be brighter than 1 pixel.
So we'll talk about Fermi a little bit more, but roughly its point spread function is about 1 degree or something. And if I take a 1 degree circle around the galactic center and a 1 degree circle around the Draco dwarf or something, I expect about 10 to the 4 times more photons from dark matter in the galactic center than from Draco. That's what I mean. And it depends a little bit about what you think the inner slope of the Milky Way's profile is and all this stuff. So that number can change somewhat, but it's thousands. It's not hundreds or tens. So what are some of the things that fall in between here or other sorts of targets of dark matter gamma ray searches that maybe you've heard about? Okay. So somewhere around here, I'm going to write clusters / groups. A group is just like kind of a small cluster, okay? Like the local group is, so the signal from those should be bigger in a lot of cases than dwarfs, at least if you stack them. Do a stacked study of these things. However, you also very much expect there to be backgrounds from these clusters. They contain a lot of gas and cosmic rays, and you might be able to generate in fact, you can generate a limit from group clusters that is not very much weaker from that from dwarfs. But if you ever saw a signal, I think you'd have a hard time convincing the community it was real without really being able to measure it with high precision. In fact, I'm going to change where this X is a little bit, because the signal really isn't that much better than for dwarfs. It's just a little bit better. All right, I have two more kinds of targets in mind.
Subhalos.
Sorry?
Subhalos.
Subhalos, okay. So these are tricky. Where do you think they belong on this plane?
Lower signal and lower background than the galactic center.
Okay.
Lower signal than groups, probably. Background's probably comparable.
So I'm gonna say that I'm gonna put huge error bars on this. I agree. It's not going to be as bright. It's not going to be as bright as the galactic center. But there are almost certainly subhalos in the local Milky Way which are brighter than dwarf galaxies. So in light of that, why don't we just study subhalos instead of dwarf galaxies?
I actually have a question.
Okay.
You were saying earlier about stacking, and it occurs to me that there's another, I guess, the thing that you could take into account, which would be the number that you can observe. So like if there's a relatively low signal, but if there's a ton of samples, then you could get a much better.
So that's in fact why clusters outperform dwarfs. You can do a stacked sample of hundreds or thousands of clusters. There are not that many known dwarf galaxies in the Milky Way. And it turns out that if you do a stack of the top 10 dwarf galaxies, and then you do it with all 50 or something, you get about the same answer. So it's really just a handful of these dwarfs that really matter. With clusters, there are more of them, and that's part of their selling point. So, yes? That's the answer to what question? I forget.
Just like, the possible sources.
Well, that would be a background, right?
Well, I mean, just you accumulate background in some, like the sun or.
Oh, okay. So, but let's say there's a bunch of dark matter in the core of the sun. How many gamma rays escape from that? 0, right? The sun is awfully opaque to gamma rays. Yeah. For neutrinos, which we'll talk about later, that's an interesting target. So yeah.
What about galaxies that are close by, say Andromeda? Lump that into the galactic center.
No, that should be along here somewhere too. Yeah, and they're not. It's not technically a cluster group. I didn't mention that because Andromeda is really like kind of the worst of all worlds. It has all the background problems that, say, the galactic center has. So it's up here, and at the same time, it signals much lower. So I don't know. I'll put Andromeda here or something. But you're right that people have considered that. So let's talk a little bit more about subhalos. It occurs to me that I just started talking about subhalos without saying what they even were. Hold that thought. All I mean by a subhalo is a clump of dark matter that is too small or had an evolutionary history so it didn't form a dwarf galaxy. So this could be something that's on the boundary of being a dwarf galaxy. Maybe it has 10 to the 7 solar masses of dark matter or something. Or it could be something with the mass of the Earth in dark matter. like a huge continuum of masses. Numerical simulations tell us that there should be a lot of these things. There should be a ton of them. And the best estimates are that the nearest brightest subhalos should be considerably brighter than dwarf galaxies in dark matter annihilation products. But yet, dwarf galaxies are definitely the more powerful probe. Can someone tell me why that is? We know where the dwarfs are, and therefore we can point our telescopes at them, right? Whereas in the case of subhalos, you just have to look everywhere, and you can never tell whether you're looking at a signal or background, and therefore the constraints you pose are quite weak. I'm sorry, I didn't ask what your question was after getting distracted. Oh.
Milky Way at high latitude, the way that
Good. So let's take this and extend it towards worse backgrounds and higher signals by calling this the halo of the Milky Way. Okay. So you can get more signal and at the expense of more background by extending the search to the halo. Okay. So because we don't know how bright the brightest subhalo is, we don't know exactly where to put it on this plot. And furthermore, we don't know where we're going to find it. So this thing also has considerable uncertainty in terms of its background. So subhalos are an interesting channel, but it's tricky to evaluate exactly what we have or haven't learned from them.
For a subhalo, you have also the problem of trying to figure out exactly what the density is, because literally the only probe there, you have to be like lensing. You normally...
Yeah, which won't tell you. That's not good enough yet. So you won't know, right? So if you saw a point source or even a slightly extended source and you were sure that thing was a dark matter subhalo annihilating, you wouldn't know whether it were a nearby small thing or a far away big thing. You just couldn't tell that apart, at least not with any realistic experiment.
Even though our galaxy center is noisier than dwarf galaxies, but the way Andromeda was better than dwarf galaxies.
Could you repeat the question? Sorry.
So even though our galaxy center is noisy than the dwarf galaxies, but we understand those noise better than dwarf galaxies. Because we don't know actually whether they are black holes or pulsars in those dwarf galaxies.
Well, so I'm going to disagree with that. I think we actually know a lot more about the dwarf galaxies because they're much simpler. And we'll talk about that as in the next hour or so.
So the subhalos, are they like just dark matter, or are there stars in the matter, or the gas?
So there's some small bit of continuum where you know something is on the boundary being a dwarf galaxy and being a subhalo, and there could be a few stars in those. But I'm really talking about something that doesn't contain stars, basically, when I say subhalo. That's what I have in mind. So there's one last thing I haven't put on here yet, which it's a really high signal and really bad background, but in a different way. I'm going to say I'm roughly in this sort of area, and it's the isotropic gamma ray background. So if you integrate the signal of dark matter annihilation throughout the universe and add it up and compare that to the high latitude isotropic gamma ray background, you could also look for signs of dark matter in this way. In that case, the equation I wrote up here, it needs to be modified to account for cosmology, like redshifting, and for attenuation. Carlos, did you have a question? I'm sorry, I cut you off.
Oh yeah, I was going to ask, what are the types of characteristics sizes for subhalos?
So, roughly speaking, the mass of a halo goes like the virial radius of that halo cubed. Okay. So, if we're in the case of 10 to the 12 solar masses, which is the case for the Milky Way, the virial radius is about 300 kiloparsecs. So let's say, I don't know, for example, we instead wanted to consider a 10 to the 6 solar mass subhalo. That's 6 orders of magnitude in mass, which is 2 orders of magnitude in radius. So this is like 3 kiloparsecs. But these subhalos get tidally stripped as they move through the larger halo and disk of the Milky Way. So what really happens is they get truncated at sub-kiloparsec scales, okay? And it depends exactly their evolutionary history, how many times they pass through the disk and things like this. So we're talking about pretty small objects. And if I went all the way down to Earth masses, then instead of going down 6, I went down 18 or so, which means that instead of talking about a virial radius of 3 kiloparsecs, you'd be talking about a virial radius of like 30 parsecs, which would be truncated down to much smaller sizes still.
Can you put some sort of bound on the upper mass of a subhalo by saying if it was bigger than this, it would have collapsed into a dwarf galaxy?
Well, they wouldn't collapse into a dwarf galaxy. It's that baryons would have fallen into it. Okay, so yeah, the baryons would have collapsed. Yes, and that, I mean, that typically is around 10 to the 8 or 9 solar masses, you know, roughly. But again, that's a hydrodynamical simulation question, not one that you can do on first principles.
What proportion of the subhalo is dark matter as opposed to baryonic matter? Do you have any way of testing this?
When I talk about a subhalo, I'm really talking about something with a negligible amount of baryonic matter. Okay, so I mean, if it had a lot of baryonic matter, then we'd call it a dwarf galaxy. Okay. That's kind of the definition that, yeah, of the two. Okay, I should draw bigger. Okay. Here?
M subhalo.
This is M subhalo. Mass of the halo scales approximately with the radius, the virial radius to the third. And then I just deduced that for a 10 to the 6 solar mass subhalo, you would expect a few kiloparsec virial radius, which would be tidally truncated to sub-kiloparsec scales. Yes?
I'm a little confused. Why, if you go to the halo of the Milky Way, you increase the background? I mean, what does that mean? You're not looking at the center anymore. So
Good.
there's all the stars. And also, why higher signal if there's
So here's the sky, okay, in galactic coordinates. This is the plane of the Milky Way, and this is the galactic center, okay? The brightest point in terms of dark matter annihilations is certainly the galactic center, but then there are roughly radial contours where the signal gets lower and lower and lower. And then there's a background, and the brightest background is emission along the plane, okay? And then there are a few point sources, some pulsars here and here, and there's a blazar up here, whatever. That's to first order what this looks like. But as you move away from the plane, you'll still find backgrounds, okay? They just fall off gently. I kind of like that picture. And if you consider what the signal to noise is here, it's much higher than, or signal background here is much higher than, say, here. Actually, that's not strictly speaking true. That's not what I mean. Sure.
So it also comes down to typically the region of interest that you study in the galactic center versus outside of the area. So you'll look at a much larger pattern of that because your backgrounds are much lower than they are at the center. So it's sort of, there's this compensating factor of your signal itself is lower than at the galactic center, and the background itself is slightly lower, but you're looking at a much larger area.
Totally agree. So the signal per solid angle or the background per solid angle might not be the right measure, but the total background increases as you increase your window.
Thank you.
Okay, so let's talk about dwarf galaxies in specific, and then we'll move on to the galactic center after that. So first of all, how do we discover dwarf galaxies? If I look at a field in some sort of stellar survey or something, I just see a ton of stars. I can't personally tell by eye when the dwarf galaxy is in the field or not. So what do you do when you look at a field of stars to tell that a dwarf galaxy is present?
But them moving kind of coherent.
So how do you know if they're moving?
Come back there for
So usually you don't have velocities on very many stars. So that's not something you can do. You can with Gaia now, but it only kind of nearby things. So.
You can look at the Doppler shifts and a bunch of different things.
You need to have velocities of Doppler shifts.
Yeah,
We don't have those, and for very many.
okay.
So, spectroscopy, which is what you need to get a Doppler shift or a velocity, requires a dedicated look at a particular telescope on some particular star. I look in some field, and there are, literally millions of stars in that field. To try to imagine measuring all those velocities is entirely impractical. So what you want to do instead is plot them on what we call an HR diagram. So roughly speaking, we have a temperature, which is really the color of the star compared to the luminosity. And the vast majority of stars evolve or fall along the main sequence, right? So this is where stars that are burning hydrogen fall in this relationship. But of course, you don't really measure a luminosity, you measure a flux, so you don't know how far these stars are away from you. So when you look at a field of stars that includes many stars at many different distances, what you find are main sequence stars that fall everywhere on this plane. You populate the whole plane. But if there's a dwarf galaxy in your field, you'll find that there's an overdensity along a particular stripe. That tells you that there's a main sequence overabundance at a particular distance. And that tells you in turn that there's a star cluster or dwarf galaxy there.
So on this type of plot, do all of these little specks follow the same contour, just shifted up and down?
Yeah, so that's right. So this is really like, I should say flux. So these stars, for example, these three, are main sequence stars at a different distance, okay? And these are main sequence stars at a different distance. The fact that there's an overdensity along some particular stripe tells you that there is a dwarf galaxy at a particular distance. So then you have a collection of stars. A typical dwarf galaxy has thousands of these stars. But you still don't know much about the system. So that's where you do the spectroscopy. Now you take the brightest members, the brightest stars in that galaxy, usually red giants, and you take a dedicated telescope, point it at it, and get spectroscopy, which allows you to get velocities. Of course, you only get velocities in the direction of the dwarf galaxy. You don't get directions in a perpendicular direction. So you can't do things like rotation curves and stuff like this. You can't map out the gravitational potential in the dwarf in the way that you might with a whole galaxy. So instead, you do the following. This is what we call a genes analysis. We're going to assume a few things, which are pretty debatable, but they're at 0th order a good place to start. We're going to assume that the system is in approximately steady state. Okay, this wasn't in a recent merger. It's not in the process of being torn apart or something like that. This is a approximately steady state configuration. We're going to assume that it's an approximate spherical symmetry, which again, probably not strictly speaking true, but dwarf galaxies, we call them dwarf galaxies for a reason. They're to 0th order spherical. And thirdly, it's assumed that there isn't any rotational support that matters in these systems. It's not that the thing is collectively rotating and forms a disk in the way that larger galaxies, disk galaxies, do. Instead, we're imagining this is a spheroid, and if this is the center of it, one star is on this orbit, one star is on this orbit, etc. This is kind of the configuration of stellar orbits that you tend to find yourself in. Okay, it's not something that has a disk or a preferred axis. You just get a system where you have uncorrelated angles of the various orbits and trajectories.
Is that not kind of related to 2 fairly closely?
You could imagine there's no rotational support and it's still oblate, for example, or prolate. Okay, so that I actually think the third assumption is probably pretty safe, but the spherical symmetry, in the sense that we have every reason to think that a large fraction of these dwarf galaxies have axis ratios of 2 to 1 in some particular configuration.
Sorry, these are assumptions on the stars in dwarf.
And on the gravitational potential that underpins their motion as well. In other words, the dark matter as well. Okay, so then I'm not going to write it down, but then you use these assumptions and you derive something called the second order Jeans equation. I decided it was too deep in the weeds to talk about in this, but you can. What this does is it determines, as a function of distance from the center of the dwarf, for an assumption about the gravitational potential, it tells you what the velocity dispersion of the star should be. And then you compare that to data and use that to constrain the gravitational potential of the dwarf and therefore the dark matter mass profile, density profile. Does that make sense? Approximately. So then you take this J factor, actually it's here. You calculate the J factor for the dwarf, marginalizing over the freedom in the C fits, and you get constraints on the J factor for a particular dwarf. And this has been done for several dozen Milky Way dwarf galaxies. I think we can move on here. Yeah, so as an example, consider the dwarf Draco. It's a classical dwarf. It's one of the oldest known, has a lot of stars, really easy to measure, a lot of advantages. The J factor, or the log of the J factor, is about 18.8 plus or minus 0.2. And now this is in units of GeV squared per centimeter to the fifth. Okay. So that means there's only a fifth of a decade uncertainty in the annihilation rate for a given dark matter model from this dwarf. This was derived under all these assumptions of steady state spherical symmetry and negligible rotation support. I think if you included those things, you'd find that the error bars will blow up a little, but they're not particularly large. There's probably a factor of 2 or maybe 3 uncertainty in the annihilation rate from a dwarf like Draco. On the other hand, we could consider a more newly discovered dwarf like Ursa Major 2. Whereas Draco is a classical dwarf, which means it existed before the era, or was not existed, it was discovered before the era of modern surveys. Ursa Major 2 is what we call an ultra-faint dwarf galaxy. These are the sorts of galaxies that are being discovered in the Sloan Digital Sky Survey and Dark Energy Survey era. Okay? And many more will be discovered by LSST in the years to come. In this case, the error bars are significantly larger, more than about 2.5 times. And I would say it's even more susceptible or more dependent on these assumptions. I think the real error bars are probably to be inflated by a larger fraction here than in this case. I would say there's at least a factor of 5 or 6 uncertainty in the J factor of Ursa Major 2. Another thing I didn't mention that can go in these error bars, which is tricky to do, has to do with the details of stellar membership. So some of these dwarf galaxies, a really good example is Segway 1, which is an ultra-faint discovered in the Sloan era. So Segway 1 has very few stars in it. In fact, there are something like a dozen or so, maybe 15 stars that are bright enough to get a velocity for. And it turns out some of these may or may not really be members of the galaxy. After all, in that HR diagram I wrote down, there are going to be some that are kind of near the boundaries, and statistically you're not sure if they're really members of the dwarf galaxy or not. So when you take that into account, it turns out your J factor you get for segue depends critically on one or two stars and whether they really are in the dwarf or not. If you include them, you get J factors of about 20 in these units. And if you don't, you can get J factors that are 15 or 16, which on a log scale, this is a factors of thousands different. So some of these are very tricky. So anytime somebody shows you a limit on dark matter annihilations from dwarf galaxies, you should bear in mind that different groups get different J factor determinations, and maybe you should widen some of the error bars that are quoted in most of these studies. Okay, so let's talk about how you'd measure these things, and in particular, I have in mind the Fermi telescope.
I'm sorry, if you have stars that you're not sure whether or not they're part of this thing, is there something else nearby that they might be part of instead, or would this just be a star that's floating in isolation, not affiliated with any?
I mean, most stars we see in the night sky aren't in a cluster or in a dwarf galaxy. They're just part of the Milky Way. Ours is not, for example. So yeah, that would be. The question is whether the thing we know it's nearby that dwarf, but we don't know if it's gravitationally bound to the dwarf, and that's the important distinction. So Fermi is a telescope that's on a satellite, or is a satellite, or it's on a satellite, that's a better way of putting it, for the last decade or so. Let me give you a kind of few key numbers. The effective area, in other words, the area that a photon hits and it registers an event, is just under a square meter. Okay. It covers about 20% of the total sky at any given time. And over a week, it covers the whole sky. It just kind of rocks across the sky. It sees photons down to energies of around 100 MeV. It can go a little lower, but it starts to lose sensitivity in the 100 MeV range. Sorry? Threshold and effective. In principle, Fermi can see very high energy photons up to a TeV or so, but the fact is the flux just runs out long before you get to that point. So there are very few sources, for example, that you see mini photons above about 100 GeV. It's just a matter of the fluxes fall off at high energies.
So that's the threshold, that's on lower or?
Lower. Anything below that is hard to measure for an instrument like this. I should also mention this is a pair conversion telescope, so the way it detects a gamma ray, so gamma ray comes in, hits some material like tungsten, produces an electron-positron pair, which travel through the instrument, and the tracker records the trajectory of that electron-positron. You reconstruct the photon direction and energy. The point spread function for Fermi, in other words, the angular resolution, is several degrees at 100 MeV, about 1 degree at 1 GeV, and about 1/10 of a degree above 10 or so GeV. So high energy photons are cleaner. You can measure their direction much more effectively. That means that images at low energy are blurry and images at high energy are crisp. Also, I should say that it has about 10% energy resolution or so. So dwarf galaxies on the sky turn out to be a fraction of a degree in radius. Okay, half a degree is a kind of typical size of a dwarf galaxy. So Fermi, except at the very highest energies, can't really resolve the detailed structure of a dwarf, at least not very well. So you can almost think of it as just being 1 pixel in terms of angle on the sky. Now, the modern analyses of dwarf searches, dwarf dark matter searches do take into account the detailed angular structure, but this is only a very modest amount of information that gets added. So let's use Draco as an example again and calculate the prospects for Fermi to see this. So the flux from Draco is going to be the same equation on the far left board. And here I'm going to integrate over whatever my dark matter model says the spectrum per annihilation is. So now this is going to be a number of photons that we're going to detect. And then here's my J factor, which we're putting in 10 to the 18.8 GeV squared per centimeter to the 5th. All right, so I'm going to plug some numbers in. I'm going to peg this to a canonical cross-section benchmark. And I am going to imagine that this dark matter model produces 10 photons above threshold per annihilation, which is not a bad estimate for a wide range of masses. And I'm going to consider a mass of 100 GeV. So now to see how many photons Fermi will see, I'm going to multiply this by the effective area by a factor of 0.2 and by 10 years worth of seconds. And this works out to be about 2.7 photons that Fermi should have detected from annihilations of this kind of dark matter particle in Draco over the last 10 years. Again, scaled to these values here, which are, a reasonable candidate to consider.
For a single annihilation, then you expect 10 photons?
Yeah, we're going to talk about that in a later lecture, but yeah, what I have in mind is you're annihilating to maybe some quarks. Those quarks fragment, produce a bunch of pions. Those neutral pions give you photons when they decay, and you add up that spectrum, and you get something like order 10 photons per event. Of course, it depends on the mass and your threshold and all these things. Sorry? 0.2 is the fraction of the sky you're observing given time. So only 20% of that 10 years was Fermi looking in the direction of Draco. That is area effective. That's an A. Yes. So that's 8,500 square centimeters. How do the prospects for Fermi detecting this kind of dark matter candidate annihilating in Draco sound? Yeah, 3 events in 10 years is not great. But really to say that, you need to know more about the backgrounds. If you had a truly background-free or extremely low background environment, maybe this wouldn't be so bad. And when we had this chart here, we said the backgrounds for dwarf galaxies were good. Let's see how good, okay? So Draco, all these dwarfs we're talking about are basically at high latitudes. So in that map I drew before, we're well away from the really problematic parts near the disk or near bright sources. But there's also an isotropic background of gamma rays. This is true everywhere. There's nowhere you can point that avoids it. So the spectrum of the IGRB, the isotropic gamma ray background, roughly speaking, has been measured to look like this. That's GV, that's TV. It falls off with a gentle, sharper than e to the minus 2 power law. And this is in units of GeV per square centimeter per second per steradian. So this is just a crude back of the envelope. But you get an answer that's kind of like this. I'm going to go down to 1 GeV because I'm going to apply that as my threshold here. And I'm going to do this in a 0.5 degree radius circle. In other words, I'm going to do the number of steradians that corresponds to a half a degree radius circle. 1 second. And then I multiply by all the numbers that I did before, and I find that this works out to about 70 photons in the Fermi data set over that period of time, compared to about 3 signal photons. You had your hand up.
When I had to just answer, I forgot what the
A steradian. So the entire sky is 4 pi steradians, so it's a measure of solid angle. So 4 pi is 36,000 square degrees or whatever. So it's just a unit of solid angle. I guess I can give you this number. So this works out to about 0.00024 steradians. So this background seems to swamp the signal, but it's maybe not that hopeless. Let's try to be a little more optimistic. So one way we could be more optimistic is by considering a lighter dark matter particle, because the screen the panel I just covered up said the signal goes like 1 over mass squared. So let's say, I don't know, 30 GeV. So that's going to gain us about an order of magnitude in flux. And let's consider a dwarf that's maybe a little more optimistic than Draco. Okay. The highest J factors that have been measured, although the error bars are big, are as big as about 10 to the 19.5. Okay, so it's considerably bigger than Draco's. And this gives us a signal of about 17 events, with a background of about 70. This would be 1 sigma would be equal to this, right? Oh, no, I'm doing that wrong. So if you observe 17 plus 70, the square root of 17 plus 70 is the error bar on that. And you see, oh, that doesn't make sense. What am I doing wrong? All right. So you would observe about 87 events in this scenario, and you would have expected 70. And this gives you about a 2 sigma excess. Okay. So the best case scenario for a 30 GeV WIMP pointing at annihilating the most favorable dwarf with the canonical cross-section we're talking about, you could hope could lead to about a 2 sigma excess. Now, how could you improve upon this? How could you make Fermi searches for dark matter using dwarf galaxies more powerful than getting a 2 sigma hint in such a search? So we know like 50 of these things, right? And 10 of them are important or so. So yes, you do a stacked, careful statistical combination of these. And when you do that, I'll just try to sketch the final result. Put it here. So I'm going to assume in this plot, as is common, that we're talking about a dark matter candidate that annihilates to BB bar. Obviously, the limit will depend on that assumption, but it's not a bad benchmark to consider. This is going to be in cubic centimeter per second units, like we're getting used to. And the limit looks roughly like this, where our benchmark model, our benchmark value falls around here, and this corresponds to 50 or so GeV. So in other words, if we're talking about a strict 2 times 10 to the minus 26 cubic centimeter per second WIMP, you know, a simple velocity independent, no bells and whistles WIMP that annihilates entirely to BB bar, and I trust all the J factors that have been reported and all these things, I find that dark matter can't be lighter than about 50 GeV. That's real information, okay? There are tons of caveats, which I've just kind of tried to emphasize. It would not surprise me if these limits move up or down by a little bit, but that being said, this is approximately the best constraint we have on this class of models at this time. I won't dwell on it, but I will just briefly mention that there are a number of the dwarfs, including some of the nearest by and most promising, that do exhibit small excesses. Most well known is Reticulum 2. This is one of the recently discovered dwarfs by the Dark Energy Survey. If you don't worry about look elsewhere effects and you only consider the known backgrounds, the excess is 3.5 or 4 sigma. But that's really the wrong way to think about it, because we know that there are unknown backgrounds. In particular, there are a lot of point sources out there that we haven't characterized, and there's some chance that one would happen to chance align with Reticulum. When you take that into account, it's more like 2.5 sigma. There's also small excesses of a similar nature from Tucana 3, Bootes 3, Tucana 4, and Indus 2. And if you include all these things together, there is a few sigma excess floating around. The good news is that that will get sorted out with some combination of more data and improved spectroscopy where you can really nail these J factors in a more compelling way.
If you have significantly, like say 4 sigma excess, would this not be in a way problematic, because it would be indicating that you were seeing more of an excess than what than the thing you were looking for was, and therefore was probably either there was something else contributing or something else was weird.
Why would it be more than?
So like if you had, we went through this thing to see how many signal events we would necessarily expect. If you were to see, say, 47 extra signal effects that were above the background, that would be significantly more than 2 sigma non-background, but it would also be more than you could really explain that integral with being different problem.
Well, so the reticulum excess in these others as well, or most of them anyway, favor something right in kind of this region, okay, which is totally compatible with everything else we know. I'm not trying to make anybody too excited about these excesses. It's very possible that these are chance-aligned blazars and some statistical fluctuations around that. I'm only mentioning it on completeness grounds, really. But there's nothing incompatible with the reticulum excess and other things that we know about dark matter.
What does it mean by estimating?
So, so the backgrounds I have in mind are point sources, okay? So the most recent Fermi catalog of point sources is called the 3FGL. And this contains about 3,000 or so gamma ray sources. These are all high significance, 4 sigma or more. Of those 3,000, about 1,000 of them we don't know what they are. Okay, they're not yet identified. And about 1,500 are either blazars or blazar candidates. What a blazar is just an active galaxy powered by a supermassive black hole with a jet pointed in our direction. So we have every reason to think that there are other gamma ray sources that are not in that catalog because they're not 4 sigma. And we don't always have multi-wavelength information that tells us there's a blazar there. So let's say there's another 1,000 blazars on the sky. They're 2 sigma blazars-ish, that sort of thing. And there's some chance that there happens to be one in that angular bin where reticulum is. You can't say that isn't possible. It is possible. You can calculate how likely it is. You can do things like blank sky tests, where you look in the field around your target, but not at your target, and you classify statistically how often you find 2, 3, 4 sigma excesses, and use that to inform your statistics. And that's what takes you from the 3.5, 4 sigma excess to the 2.5 sigma excess by characterizing the blank sky in this way.
So that bound is chi goes to BB bar is way south.
Why did I write BB bar?
Yes, and where you got?
Well, so in this equation on the very top there, where I said the number of events from Draco, that integral has to assume something about how the dark matter annihilates. Okay? So I could have written down other things, okay? And in the Fermi paper, they write down this and one other model. Okay? I think they go to taus as well. And some papers include several others. Turns out that, go ahead.
In this band is from Fermi itself.
Yeah, this is the Fermi collaboration's most recent bound on this. You get different answers depending on what you annihilate to. You could imagine a dark matter candidate that annihilates entirely to neutrinos, and there would be no constraint. Or electrons, or, well, actually electrons will have a constraint, it'll just be weak. So you have to assume something about how the dark matter annihilates. It turns out that if it's annihilating hadronically, it doesn't really matter which kind of quark you make. And if it's annihilating the gauge bosons, it doesn't really change things very much. If you're annihilating the Higgs, it doesn't really change things very much. The cases where it's really different are neutrinos and charged leptons, that you can get very different answers in those cases. And later in this week, we'll talk about the kind of why dark matter might annihilate to BB bar and what are the kinds of underlying particle physics models that lead to different indirect detection signatures.
The photons are coming from the BB bars.
So you produce a pair of Bs. They're highly boosted because the dark matter is much heavier than the B. That B then quickly fragments and hadronizes. So it usually decays, for example, to a charm and some other stuff. And pretty soon you have a bunch of neutral pions in that cascade, and those neutral pions decay to gamma rays.
What if the standard model particle that you annihilate to is heavier than a dark matter particle? So like, if it's something like the Higgs and you have some fairly light dark matter.
So that will be highly suppressed by kinematics. However, you could imagine going to a slightly heavier state in an off-shell way as long as it decays quickly enough. But that will be suppressed. So that's not usually something you find in most models, although it is a logical possibility. Usually when people talk about annihilation to something like Higgs, what they have in mind is a dark matter candidate that's heavier than 125 GeV. All right, so that's all I have to say about dwarfs. I'm going to go on to the galactic center unless there are questions. All right. Okay, let's start with what we think we know about the distribution of dark matter in the halo of the Milky Way. I've just written down what's known as the Navarro-Frank White profile, or NFW. This is a exceedingly common parameterization for the density of dark matter in halos, and it comes from numerical simulations. There is plenty of reasons to think that this is an imperfect description of how dark matter is really distributed. And it's also probably the case that no two halos are exactly alike. Some will have a slightly sharper cusp or distribution in the middle. Some will have a flatter one. The fact is, this should just be thought of as a 0th order model, but it probably gets the big picture approximately right.
Is R supposed to sort over this?
It is the scale radius. Yeah, that would be weird, right?
I was wondering, it's going to ask the same one.
In the case of the Milky Way, the scale radius is about 20 kiloparsecs. So if I just plot this, the density goes like 1 over r inside of this, well inside of the scale radius, and then transitions to 1 over r cubed well outside of the scale radius. And then somewhere way out here, it gets truncated at what we call the virial radius, which is a few hundred kiloparsecs in the case of the Milky Way. In this part of the Milky Way's halo, we don't have a lot of information to rely on. We have some, but not a lot. It's possible that this, the slope in the inner, say, 1 or 2 kiloparsecs is substantially steeper than 1 over r. Maybe 1.2 or 1.4. Those are perfectly reasonable numbers. It's also possible that the slope flattens, maybe to 0.8 or 0.5 or something in that region. The fact is we don't have much dynamical information to make that determination. And the reason is that there's a lot of mass and baryons here. Okay? Out here, the galaxy is dark matter dominated. Where we live, about here, there's a similar density of dark matter and baryons. As you move inward, baryons are more and more important. And therefore, unless you know, for example, the baryonic density to very high precision, you can't really infer dynamically the presence of the dark matter density in that part of the sky.
Question.
Yeah.
So, how rapidly does the black hole at the center of the galaxy get dark matter? And can you count that black hole as being dark matter for our purposes here? And how does that interact with this plot?
Yeah. So the mass associated with the black hole is only important on extremely small scales, smaller than we're going to be concerned about here. So, I mean, offhand, okay, so let's do a back of the envelope, okay? Let's ignore the scale radius and say the density of dark matter is going to be the local density times something like this. This is the local radius over the radius. So now let's say the mass in dark matter within some radius r is going to be this, where I'll then write this as follows, right? This guy's about 0.3 GeV per cubic centimeter. I need an 8 kiloparsecs and a 4 pi. And then the integral turns into r dr, which I guess I should put primes there, r squared over 2. So if I put a kiloparsec in, I'm sorry, I'm running out of board space, but this mass is going to be, I'm going to drop some order 1 factors, but GeV per cubic centimeter, kiloparsecs cubed. This is about 10 to the 21 cubed. And what's a GeV to kilogram conversion? 10 to the 27 minus 27. So we're going to call this Oh, that can't be right. What did I do wrong? 10 to the 40? Well, 63 and 56. Okay, good. This is about 1 million solar masses within a kiloparsec, which is just wrong. I was supposed to prove to you that the dark matter abundance was way higher than the mass of the black hole, and I got the mass of the black hole. Does anyone catch the error I made? Oh, I see a bunch of things. I dropped 4 pi times 8, which is a factor of 100. That's pretty important. So 8, 10 to the 8 is 100 times more mass than in the black hole. And therefore, we can not worry about the dynamical effects of the black hole to first approximation. And the baryonic mass that's not in the black hole is bigger than this. So another way you can...
Pressure preventing it from falling into the black hole. One of the things that puzzles me about dark matter is it doesn't have that pressure keeping it from collapsing in. I'm not entirely certain why the black hole just doesn't eat it all.
Well, I mean, it does to a certain extent. There is adiabatic accretion onto the black hole, but for the most part, a dark matter particle has a certain amount of angular momentum, and that prevents it from getting close enough to the black hole to be swallowed. Okay. Okay, so let's just do a back of the envelope estimate where we're going to calculate the annihilation rate in the inner part of the Milky Way, and this is the relevant part that has to do with the density distribution. And this is going to look similar to the calculation I did. That's the local density. And let's, in this case, integrate out to 2 kiloparsecs. So this is going to calculate something that's proportional to the annihilation rate within the inner 2 kiloparsecs. Sure.
I think R squared over R.
I don't think so.
Yeah, no, it's square.
Because the density profile is squared. So the integral over the inner over to a 2 kiloparsec radius sphere of the density squared works out to be about 7.6 times 10 to the 66 GeV squared per cubic centimeter. So the number of photons per annihilation times the annihilation rate over 4 pi times the distance squared. So this is going to be the flux now. We've seen this before. And now you see why I calculated that. And when I put in all the numbers, this works out to roughly, putting 10 in there. Works out to roughly 3,000 photons per square meter per year. Compare this to a dwarf galaxy. We worked out for Draco. This was for the same parameters. We were getting something like 3 events over 10 years. Okay? So this is nearly a factor of 10 to the 4 higher flux This is why we study the galactic center. It produces a ton of dark matter annihilation products. If dark matter annihilates, of course. Of course, that's only half the story. Like we started the lecture with, we had this plot, this chart that showed the dwarfs were in one kind of extremum where you have a relatively small signal, but controllable and small backgrounds. We knew that this signal was going to be a lot larger. We just showed that it is, but the backgrounds are much, much more severe, and that's what we'll talk about tomorrow morning. The backgrounds and how we try to mitigate those and do sophisticated analysis to try to separate these things. Since I have 1 minute left, just what's the information that I have at hand that I can, in principle, use with a gamma ray telescope to distinguish signal from background? What information can I build that argument based on? Total generality.
Spectrum morphology.
Okay, good. So you have angular and energy information. Okay, those are going to be the two things we try to put to use. It turns out astrophysical processes give you at least, if not predictive, at least constrained angular distributions and spectral distributions, and they're different from those predicted from dark matter in most cases. Any questions?
Shouldn't the cross-section be
Yeah, it should. -1. Thank you. You're totally right. Yes? The scale radius? No. It should be a universal profile that doesn't depend on anything other than the dark matter's cold and collisionless.
So if I imagine I have more massive dark matter particle, I would imagine it will be more concentrated considerably.
So it turns out that's not true, and it's you can understand it from a perspective of freshman physics, right? If I took the planet Mercury and I replaced it with something 100 times more massive, but with the same velocity at that given moment, would its orbit change? No, right? An object follows the same geodesic regardless of its mass. So when people do numerical simulations of dark matter, they don't specify anything about the mass of the particle, or for that matter, really its interactions in most cases. You just assume that the only force acting on it that matters is gravity, and you assume it started out in a cold configuration. It froze out non-relativistically. That's all you have to assume.
Is it a coincidence that scale radius will be the type?
No, it's not a coincidence. If the scale radius had been bigger, okay, then you would have.
Maybe a big core, essentially, right?
Sorry, say again?
It would look like a core.
Yeah, or at least a flatter profile.
What is a scale radius?
Well, the scale radius is that point in this plot where the slope transitions from 1/r to 1/r cubed. It's just a phenomenological thing. I don't know. Originally I said no, it's not a coincidence. The scale radius sets the size of the baryonic stuff, but I'm not strictly speaking sure that's true right now. I have to think about it a little bit more deeply before I answer your question. Ask me again later. All right, let's go to lunch. Thank you.